Hi, everybody. This is Dr. Phil from Med Pathway. We're doing a workshop on kinetics with focus on enzyme kinetics. So let's take a look. So basically, chemical reactions always result in changes in energy that result in formation or dissociation of bonds. I think we all know that. What kinetics does, it deals with how to perform these reactions on appropriate timescales and how to find a pathway that can actually accomplish this. Now, whenever we think of kinetics, we also have to think of thermodynamics. Now, we're not going to focus too much on thermodynamics as we're going to discuss it in more detail later. But what we should recognize is that thermodynamics tells us whether or not we can actually do a reaction. Is it spontaneous? And if so, how much free energy can we harvest from the chemical bonds to do work in other reactions? The most common thing people discuss is diamond to graphite. The conversion will occur over several thousand years, so it is quite slow, but it's thermodynamically permissible. So kinetics tells us how fast reactions go from reactants to products. Thermodynamics describes the amount of products at equilibrium. And in a dynamic equilibrium, the forward reaction equals the reverse reaction. And so there's no observable change over time. And you should compare equilibrium to the steady state. During a steady state situation, you do get changes in product over time, and you have to put energy into the system. Our body is more likely to be at steady state than in equilibrium. When we talk about Gibbs free energy in thermodynamic terms, we always look at this equation here, delta G naught equals delta H naught minus T delta S, where the naught is referring to a standard condition because you always measure this against a standard. And so if the reaction is spontaneous, the delta G will be less than 0. So what you see here is a typical reaction coordinate, the progression of a reaction over time where you plot free energy as a function of the progress of the reaction. And so we see the reactants over here and the products have a lower energy. So that means the reaction's exergonic. It's going to release heat into the atmosphere. If the product was higher energy than the beginning reactants, then it's going to be endergonic. It'll actually absorb heat from the environment. And what you see in this particular case is that there's two pathways to make the product. So you see a transition state here that is a really high energy one. And what you see here is a lower transition state energy. This is the activation energy, EA. This is the Gibbs free energy of activation. There's similar terms. You probably won't have to distinguish them much on the MCAT at all. And so what we see then is that a catalyzed reaction will have a lower activation barrier or a Gibbs free energy of activation. And what you can do then is come and make your product. So we all know that reaction rates depend upon temperature as well as things like the frequency of collisions. We know that for reactions to occur, things have to come together and collide. And so what people have come up with is the Arrhenius equation, which is something that you should fundamentally memorize for the MCAT. So as we go through MCAT practice, what we're going to do is constantly identify equations that you should memorize and write down. Now let's take a look at the Arrhenius equation. Here we have a rate constant K, and it equals a frequency factor known as A, or the Arrhenius factor. This is describing how a typical molecule will interact with another molecule, how frequent it'll interact and collide. And that is equal to, so K equals A times E to the minus EA, the activation energy, as we just saw, divided by R, the gas constant, over T. And so what you should be aware of is that many of these equations get manipulated algebraically into more manageable equations. And in this case, we can generate a y equals mx plus b format of the equation when we start bringing in logarithms. And what this allows us to do is to plot log of k over 1 over t, where the slope is negative EA over R. And this is actually how you can determine activation energies. So kinetic versus thermodynamic controls on the AAMC content outline. And this reaction here is a classical example. So what we have is 1,3-butadiene plus HBr, and it gives you a 1,2 addition product or a 1,4 addition product. And you should remember from Seyssev's rule, that is what you have addition to alkenes that follow Markovnikov's rule, the more substituted alkene is the most stable one. So the mechanism of the reaction is that the pi electron will attack this proton here, generating a bromide anion, and you have this common intermediate that can then be converted into one of the two products, the 1,2 addition or the 1,4 addition product. And it turns out that if you conduct this reaction at different temperatures, what you see is strikingly different yields. So for example, at 0 degrees, you get 70% 1,2 addition, or in 30% thermodynamic, or the 1,4 addition. So it turns out that the 1,2 addition is the kinetically favored product, and the 1,4 addition is the thermodynamically favored product. And we know it's the most stable product because it's the most substituted according to Seyssev's rule. Notice that when you do 40 degrees, you get the reciprocal type of yields. So exactly how does that come up? Let's take a look. So what we have then is a reaction coordinate diagram over here. And so the very first step, what you have is the free energy. This is the proton transfer. This is the alkene grabbing that proton, and both products must go through this step. So there's a common step, and what they form is the carbocation intermediate that I showed you here. This is the common intermediate. And now the reaction diverges because what you have then are two different transition states. So over here, what you have is a primary carbocation, which has a higher energy. And over here, you have a secondary carbocation, which has a lower energy. And this is the step where you get the bromide anion doing a nucleophilic attack. And what you see is that you actually make the products. So what we can conclude is that reactions in where there's multiple products, we can get a kinetic product and a thermodynamic product. The kinetic product is the one that's formed the fastest, but it's not the most stable product. Now, there are reactions where the kinetic product and the thermodynamic product are the same. Now, kinetic products dominate when the reaction is irreversible, and that's at low temperature. So the reason why this reaction be irreversible is because there's not enough energy to come back the reverse way and get over these activation barriers. But accordingly, there's enough energy at the low temp to overcome the proton transfer barrier. Thermodynamic reactions predominate when there's enough energy into the system, so it's reversible, and that's at high temperature. So here's an example of kinetic control that uses arsenic. This is a basis for arsenic poisoning. So this is a glycolytic reaction. This is 1,3-biphosphoglycerate plus ADP and inorganic phosphate gives you 3-phosphoglycerate plus ATP. This is the step where you make ATP by substrate level phosphorylation and glycolysis. And so we remember that what happens here is that you have a high energy phosphoanhydride bond, and you hydrolyze it, and you transfer that over to ADP to make ATP. And so the hydrolysis, the energy released upon hydrolysis, is large enough so that you can adequately couple it to ADP to make ATP. But the reaction kinetically is slow, so you need time to do it. Now, what happens is that when you have arsenic poisoning, recognizing that arsenic is below phosphorus on the periodic table, and so therefore the enzyme thinks it is the same thing. It doesn't recognize there's a difference because the chemical properties are very similar for things that are in the same column when you go down. Now, but there's a difference when you hydrolyze the arsenophosphate bond. What happens is that it's so fast, there's not enough time to couple it to the synthesis of ATP, and you get no substrate level phosphorylation. As a consequence of that, you actually lose energy in glycolysis. So what we see is that despite the fact that both steps are thermodynamically permissible, one is fast and one is slow, and the biological consequence is that you don't make enough energy. Now, we speak of reactions in terms of reaction order, and this describes a relationship between the reaction concentration and the reaction rate. And we'll take a look at zero order reactions, first and second order reactions. Those are the most common ones. And in a zero order reaction, the rate law is R equals K, which is R equals the rate constant. Notice that the rate of the reaction is not a function of the concentration of substrate. And there's numerous scenarios by which this could occur. And one that's commonly discussed is the metabolism of ethanol. So what you see here is that ethanol is going to be oxidized into acetaldehyde, and NAD will be reduced. And this occurs by the action of alcohol dehydrogenase, a hepatic enzyme. And now different people from different cultures and different genetic backgrounds will have various levels of alcohol dehydrogenase or mutations in the gene that don't allow us to actually adequately metabolize alcohol. So if you take a look at the rate of oxidation of ethanol, what happens is that the reaction rate doesn't change as a function of time until you're completely depleted of the ethanol. And then what you see is you fall off the cliff here. And so the rate of oxidation is not determined by the concentration of ethanol. It's actually primarily determined by how much enzyme you have available in your liver. Because what happens when you drink the alcohol in many cases is that the alcohol rushes to the liver and it saturates the enzyme. Okay, and so the enzyme can only handle so much at a time, and you're presenting it with the saturated amount. We'll see another zero order reaction in a moment. So a classical telltale signature of a zero order reaction is that the ethanol concentration is going to change in a linear fashion as a function of time. So we'll take a look now at a first order reaction, and that's where the rate equals the constant times the concentration of substrate A. And so it's first order, so the rate is proportional to the concentration of one of the reactants. Now, people commonly integrate this and generate a formula where the concentration at A is equal to the initial concentration of A times e to the minus kt, where t is time and k is the rate constant. Notice that what you have is some sort of exponential function, and you can see as a plot of concentration over time, you get a decay pattern that looks like this. Now, if you were to take the log of the concentration, then what you would get is a linear relationship of concentration versus time, where the slope is minus k. I definitely think that you guys should be able to plot these out or to recognize what the slopes are and what the lines look like for zero and first order. But the reality is that in many cases, if not all, you have to experimentally determine the actual rate law. So here's a hypothetical example right here. This is A plus B going to C. And the question then is, well, what's the order of reaction and what's the rate law? Well, we know the general rate law is written as R equals K times the concentration of A to the M power and B to the N power. And what people do is a series of experiments. In this case, we see 4 experiments where we vary the concentrations of A and B and calculate the initial rate. So if you compare experiment 1 to experiment 3, for example, what we've done is we've doubled the concentration of A from 0.4 millimolar to 0.8 millimolar, but we held B constant. And what we see happening is that when we double the amount of A, we actually go from 0.009 to 0.036. We quadruple the initial rate of the reaction. And so what you can see happening then is that this exponent of A is going to end up being 2, because we doubled it and we went up a factor of 4. So 2 squared is 4. Now, if you compare A versus B, when you have A constant 2 versus 3, and A is 0.8 twice, and then B goes from 0.2 to 0.4, the rate stays the same. So the reaction rate doesn't depend on the concentration of B. Now, you can look at the table and make those kind of assumptions, or you can actually mathematically determine the same thing here. And what you see over here basically is that you get a 4-fold effect, as we saw before. This is 1 over 4. So what happens then is that this rate law is R equals K times A squared. It's second order, but it doesn't include the concentration of B. That is, B does not determine the rate of the reaction. And so you can't look at this reaction, A plus B to C, and say that it's second order i.e. R equals K times A times B. You can't do that. You have to experimentally determine it. So how can you get a reaction like this to actually give you R equals Ka squared? Well, imagine, for the sake of argument, that A is a monomer of a protein and it has to dimerize with itself. So it forms a homodimer, and then that homodimer actually then can react with B. So the formation of the homodimer would be the rate limiting step. And this is what a second order reaction looks like, is concentration versus time. It's a much more steeper curve. And so here's actually a table that you should probably commit to memory for rate laws of 0, first, and second order. I've also put the half-lives in there as well as the units. We know the MCAT is obsessed with units, so you should definitely keep units in mind. So the most common thing you'll see with respect to enzymes is Michaelis Menten kinetics. And so this is an enzyme plus a substrate gives you an enzyme substrate complex, and this goes to enzyme plus the product. I have K on, K off, and K cat, and they're also seen as K1, K minus 1, and K2. So there is no K minus 2 because of Michaelis Menten kinetics. The assumption is that the back reaction is essentially negligible. What people have done is they've taken this expression and they've generated this formula where the velocity, or the initial velocity, equals the maximal velocity times the substrate concentration divided by Km plus S. You should 100% memorize this formula for the MCAT. And over here, what you can do is plot velocity versus substrate, and you see this typical saturation curve here. And notice that at the top, when you add more substrate, the velocity of the enzyme, the maximum velocity of the enzyme, doesn't change. That is a zero order reaction because we saw that earlier. So there's a couple things that need to be explained and you should definitely understand. The first one is the Km, the Michaelis constant. The Km is defined as the concentration of substrate at 1/2 Bmax. Perfect. But it also represents the inverse of affinity between the substrate and the enzyme. That is, the higher the Km, the lower the affinity between enzyme and substrate, and vice versa. Now, the Kcat over here is the Vmax divided by the total enzyme. It's called the turnover number. So the higher the Kcat, the more turnover, the more enzyme products will be formed as a function of time. Now, catalytic efficiency is called Kcat over Km. And so the higher the catalytic efficiency, that is, the more efficient the enzyme is in making products. So remember, if the Km is inversely related to the affinity constant, that means a low Km over here and a high Kcat gives you enzymes with really high catalytic efficiency. And some enzymes have the ability to be so fast that they get close to actual diffusion limits. So the Fick's law of diffusion predicts that things can come together in solution at a maximal rate. And some enzymes like carbonic anhydrase get pretty close to being diffusion controlled. So we can manipulate the Michaelis-Menten curve. And when we do that, or excuse me, equation, when we do that, we can get a y equals mx plus b, and we formulate what's known as a Lineweaver Burk plot, or a double reciprocal plot. Because when we calculate or graph 1 over v versus 1 over s, what we can do is get a linear relationship such that the y-intercept is 1 over v max and the x-intercept is -1 over km. You should 100% remember those intercepts in a Lineweaver Burk plot. So we'll take a look at some types of inhibition now. The first one, the simplest one, probably the most important one, is competitive inhibition. And the reason why, you guys, is because many enzymes that are pharmacologically targeted for therapeutics in medicine are actually competitive inhibitors, as well as receptors for that matter. So what we have then is we have an enzyme plus an inhibitor gives us an EI complex here, okay? And then EI plus the substrate can ultimately compete out the inhibitor. So what we see then is as we add more substrate, we ultimately restore the maximal velocity, which means that competitive inhibition by definition must be reversible. So over on the left panel, we have more inhibitor than substrate. okay? But as we add more substrate, we swamp out the actual inhibitor, and so then the substrate outcompetes it, and you restore the maximum velocity. So in a Lineweaver-Burk plot, competitive inhibition will always have an overlapping common y-intercept value. But what happens to the Km? Well, if there's more inhibitor than substrate, it seems to me that the substrate's affinity for the enzyme is actually been reduced because the inhibitor's in the way, and as a consequence, the Km increases. There's also non-competitive inhibition. And in non-competitive inhibition, the inhibitor binds to an allosteric or a site outside of the active site. So what that means is that the substrate binds under normal conditions, normal affinity, so the Km remains the same, which is interesting. But what you have then, the inhibitor is influencing the capacity of the enzyme substrate complex to actually form product. And so what happens then is that the Vmax actually is lower. And what you see here on the Lineweaver-Burk is a lower Vmax, because 1 over Vmax, so it's a higher y-intercept, but the Km intercept on the x-axis is the same. We also have a phenomenon known as uncompetitive inhibition. And in uncompetitive inhibition, the inhibitor actually binds to the enzyme substrate complex. So think about when an enzyme binds a substrate, there's going to be some sort of conformational change. And it's conceivable that that conformational change will actually open up a binding site for an inhibitor. And when you do that, what you generate a new equilibrium. That is, the ES plus I gives you ESI. And what's happening then, when you have a new equilibrium, you can see that some of the ES will be diverted from its ability to form a product. So that means the Vmax will be reduced. But also what you're doing is, as you're pulling ES out of the system up here, that means that you're forcing more of the reaction to move to the right, and that's a Le Chatelier's principal argument. And so as a consequence of that, the Km actually decreases because the affinity gets higher from a Le Chatelier's principal argument. And what you can see over here is that you get a decreased Km as well as a decreased Vmax on the Lineweaver-Burk plot. And so what you can do is you should be able to think about what these look like. You should be able to draw all these out for each individual mode of inhibition. They're pretty important. Okay, so there's another type of inhibition that's called mixed inhibition. Now, as the name implies, a mixed inhibitor, it has mixed feelings. In fact, on the one hand, it can be competitive and bind to the enzyme's active site, as you see over here. And on the other hand, it can bind to the enzyme substrate complex, and it can be uncompetitive. And so in this case, it has mixed, and it's changes in the Km and the Vmax on the Lineweaver-Burk plot. Now, whether or not the Km goes up or down depends upon whether or not the inhibitor favors the active site or favors binding to the enzyme substrate complex. In many cases, the inhibitor will have a bias towards one or the other, and so it can actually go up or down. And so here we see the actual table that you should 100% commit to memory and understand, as we discussed, how these things actually work at the enzyme and kinetic level over here. So we'll talk about some reactions now. We're going to look at SN1 reactions, which is a common staple of the MCAT. This is substitution nucleophilic first order reactions. And the rate law is the rate equals K times an electrophile, and it always goes to a carbocation intermediate. So let's talk about carbocations really quick. So what do we know about carbocation stability? Well, we have to think about what carbon is. Now, carbon is neither electronegative nor electropositive. It wants to be neutral. So anytime you make carbon positive, you piss it off. And so what do you do to an angry carbon? Well, what you do is it's going to be highly reactive. In this case, it's an electrophile. So a tertiary carbocation will have 3 alkyl R groups attached to it. But the electrons in these CR bonds are not evenly distributed, but rather there's an inductive effect such that the alkyl group is sharing the electrons more with the carbon. So carbons pull the electrons toward itself, and by doing such a thing, it's reducing its positive charge. It's more towards neutral. That makes it more stable than a benzyl. So a benzyl carbocation, this can be stabilized by resonance where these electrons over here can come out, and that means that this positive charge on the carbon is also going to be moved around by resonance. So that what happens is the positive charge on the carbon is shared by multiple carbons within the ring system due to resonance, and as a consequence of that, no one carbon experiences a full positive charge. The same argument applies to allylic. There's also secondary, there's primary, there's methyl, and the least stable of all is a vinylic or a vinyl one. So how does SN1 work? Well, a classical thing is a tertiary alcohol for SN1. So whenever you're thinking about SN1 and SN2, you should look at the substrate and ask, is this a permissible substrate? A tertiary alcohol is going to be very conducive for an SN1. And so here's a tertiary alcohol right here. And you do this reaction in a polar protic solvent under acidic conditions. And what you do is you protonate the hydroxyl to make water. And what's going to happen is the water is going to leave. Okay, and water is a great leaving group. It's certainly a better leaving group than a hydroxyl. And so how do you know that? Because the weakest base is always the best leaving group, because bases don't want to share their electrons, right? So this doesn't share its electrons very well. If you're a weak base, you don't share electrons, so the bond is easier to break. But breaking a carbon-oxygen bond here isn't an easy feat. You actually have to put energy into the system. So how does this actually occur? Well, it occurs in a polar protic solvent. So what's a protic solvent? A protic solvent is something like water or methanol or an alcohol like ethanol. Has an OH that can hydrogen bond. And what you do is you create dipole interactions here, and the energy from the dipoles can be sufficient to actually break this bond right here. And as a consequence, you release water, and now you have a tertiary carbocation, okay? So you formed an electrophile. The reason why the SN1 rate law is R equals K times an electrophile, the rate limiting step is the formation of the actual electrophile. In solution, you have generic nucleophiles. In this case, it could be bromine, bromide, or some other halogen, etc. And they're just waiting around for an electrophile to form. And when they see the electrophile formed, they notice that it's sp2 hybridized. So it's actually planar, which means that you can have a nucleophile come in from the top, or you can have them come from the bottom of the plane to attack that electrophilic center. And when you do that, you actually form different bonds. And now you should think about stereochemistry. That is, you can get a racemic mixture from this reaction here when you think about the actual absolute configuration at that carbon. Assuming that these R's are all different, then you have 4 different things bound to an sp3 carbon. That's actually a stereocenter. And so implicit in understanding the SN1 mechanism is to understand stereochemistry. We're not going to do very much of that right now in this discussion, but you can go to our website. We have an awesome stereochemistry diagnostic exam and a lot of videos that explain that as well. That's the mechanism from SN1. What about SN2? Substitution nucleophilic second order. This is where the rate law is a function of the K constant and electrophile times a nucleophile. You need both of them to actually get the reaction to occur. And so now we take a secondary alcohol, and recognizing that secondary alcohols could also be substrates for SN1, but what we recognize is that this occurs in a polar aprotic solvent here, which would not favor the stability of carbocations. Aprotic solvent would be something like acetone. It's a ketone, it has a carbonyl group, but it doesn't have an OH, it's not a hydrogen bond donor. And so in the presence of a nucleophile, what can happen is you get this backside attack on this electrophilic center here. It's not a full positive charge here, but since oxygen is so electronegative, it's pulling the electrons toward itself because it doesn't want to be positively charged. There's nothing worse you can do to an electronegative atom like oxygen than to make it positively charged. It's unstable, it's reactive. So as a consequence, what happens, the nucleophile gets to the backside attack here, you form a transient pentavalent intermediate, and since you come from the back, you make a product, a substitution product, where you've replaced the OH and you now have the nucleophile bound, but the conversion or the configuration, excuse me, has been inverted. So if this was an R, that's now an S, or vice versa. So here's a table summary of SN1 versus SN2. You should 100% know all this for the MCAT. So we have a really interesting passage we're going to do as a workshop where we have the farnesylation enzyme, and that actually goes through either an SN1 or an SN2. We're going to give you some data and have you work through it. It's quite challenging because it'll make you apply all these concepts. So it's farnesylation. So what we see with SN1 is that the rate is K times an electrophile. It's polar product. The order reactivity is tertiary, secondary, primary. We go through an sp2 carbocation. We always have to think about stereochemistry, and we're not going to discuss the carbocation rearrangements, but we have a lot of that as diagnostics on our website. SN2, notice how the order reactivity is the inverse of that, because if you have a tertiary carbon, for example, then you're going to have a lot of bulky groups that are going to get in the way of that backside attack. Inversion of configuration, no carbocation rearrangements, no carbocation intermediate. So now what we're going to do is we're going to do a couple workshop passages. And so I think that